Something just happened at the very edge of our solar system, and if the early data is right, Voyager 1 may have interacted with 3I Atlas in a way no one thought was even possible. Before we break this down, hit subscribe. You're going to want updates on this one. This video explains exactly what NASA is seeing right now. Why Voyager 1 was even close enough to detect anything, and why some scientists inside mission teams at the Jet Propulsion Laboratory believe this might be the strangest interstellar event since Oumuamua. And as we go deeper, you'll see why researchers are now comparing this moment to earlier anomalies buried in Arecibo's old radio archives and the magnetic field signatures Voyager recorded when crossing the heliopause in 2012. Something about this new data does not match the models, and that question is what the world is now watching. To understand what's happening, we need to start with Voyager 1 itself. Launched in 1977, it wasn't designed for deep space interception of anything. It was built for flybys of Jupiter and Saturn, and then it was supposed to fade out quietly. Instead, its instruments just kept working. Sure, they're old, and the team at NASA's Deep Space Network has to fight to decode every bit of telemetry, but the spacecraft is still sending real scientific measurements. Plasma waves, magnetic field strength, charged particle density. These are the things Voyager still senses, even now. And that's one of the reasons scientists were caught off guard when they noticed something unusual. In late 2025, several observatories, including the European Southern Observatory, the Vera Rubin Observatory, and of course NASA's own network, confirmed that 3I Atlas was approaching the inner solar system on a trajectory unlike any typical comet. It wasn't following the predictable gravitational curve we expect. It wasn't shedding dust the way normal icy bodies do. It wasn't heating up according to the models. Even the James Webb Space Telescope picked up spectral readings that didn't match standard comet chemistry. At first, researchers thought it might be a fragmented object, or even a carbon-rich super-volatile body like 2I Borisov. But the numbers wouldn't line up. The Harvard-Smithsonian Center for Astrophysics publicly stated that 3I Atlas does not currently fit any known classification. That's an unusual statement from an institution normally cautious about speculation. And while all of that was unfolding, someone at JPL made an observation no one expected. If you map Voyager 1's path, which is basically a slow escape line away from the Sun, and you map 3I Atlas's inbound trajectory, the two don't intersect physically, but their regions of charged particle influence overlap, barely, for a few days. A tiny window, but a window that mattered. That overlap is what triggered NASA to schedule a small adjustment, a reorientation of Voyager 1's high-gain antenna. Not to contact anything, just to measure the shifting particle environment as 3I Atlas moved into that zone. A simple test, a routine experiment, something the public wasn't told about until after the anomaly happened. Because when Voyager 1 turned, the plasma wave instrument picked up something that shouldn't have been there. Not a signal, not a message, but a repeating pattern, a modulation in the noise floor with timing that exactly matched the moment 3I Atlas crossed Voyager's heliospheric longitude. Even stranger, the pattern was similar to earlier readings Voyager recorded decades ago around Jupiter's magnetosphere, except this new version had a tight mathematical spacing that didn't look natural. The team cross-checked it with Arecibo's legacy recordings of plasma turbulence and found no match. They checked against Hubble's older spectrographic noise and found no match. They checked against Voyager's own hardware degradation models again, no match. Something external had changed the environment around Voyager 1. And that's when the question started. If Voyager didn't send the first interaction, then what did? To break down what that means, we need to look at something most people forget. Voyager 1 may be old, but it's still one of the most sensitive instruments humans have ever placed in deep space. Its plasma wave detector can hear tiny disturbances in charged particles, basically listening to the weather of space. Normally, these disturbances come from solar activity or the shock waves of interstellar gas clouds. They rise slowly, smoothly, and predictably. But the modulation Voyager recorded during that brief window near 3I Atlas wasn't smooth. It wasn't gradual. It wasn't even random static. Instead, it rose in sharp steps, like someone turning a dimmer switch up and down in perfectly spaced intervals. That immediately caught the attention of the Deep Space Network engineers at JPL. They ran the numbers again, checking for solar flares, coronal mass ejections, or distant supernova shock waves that could cause similar effects. Nothing matched. The sun was quiet. No recent solar eruptions aligned with a timestamp, and nothing else in the interstellar neighborhood could have produced a sudden structured rise like that. The more they looked at it, the more it resembled electromagnetic interference, except coming from deep space where nothing human exists. The European Southern Observatory reviewed the data as well. Their team at Paranal Observatory compared the pattern to turbulence signatures captured by the Very Large Telescope's adaptive optics system and again found the same conclusion. This wasn't turbulence, it was too clean. Meanwhile, scientists at the Harvard-Smithsonian Center for Astrophysics cross-referenced the modulation with historical records from Hubble's spectrograph, thousands of hours of archived instrument noise. Still nothing. No natural match, no mechanical match, no cosmic match. That led to an uncomfortable idea. This disturbance didn't come from Voyager 1. It came from the direction of 3I, Atlas. But that raised a bigger problem. Voyager wasn't close enough for any signal to be detected. They weren't talking about radio waves. Voyager's antenna never detected anything like that. What moved was the charged particle environment itself, as if something passed through it. And right here is where many scientists step back, because if 3I Atlas did influence the particle environment, it means one of two things. Option 1, 3I. Atlas has an extremely strong magnetic field, something no comet has ever shown. Option 2, 3I. Atlas is interacting with the solar wind in a way we have never seen before, similar to how metallic objects behave in plasma chambers at Stanford during early Bracewell probe simulations. Both options are strange. Neither fits the usual model. The Vera Rubin Observatory, which specializes in wide-field sky surveys, reported that 3I, Atlas's brightness curve, fluctuated in sharp pulses, almost like it wasn't just reflecting sunlight, but reflecting it off something structured. Again, nothing conclusive, but the timing overlapped with the Voyager modulation. That coincidence is what pushed researchers to take the anomaly seriously. Because if two different instruments, one near Earth, one at the edge of interstellar space, detect unusual behavior at the same time, the probability of a meaningless coincidence drops fast. And that's why NASA quietly expanded the monitoring window, bringing in everything they could. Hubble's old ultraviolet datasets, James Webb's mid-infrared readings, ground-based radio telescopes, even some old Arecibo data models to build a complete picture of what 3I Atlas might be doing as it moves inward. But here's the part that truly made scientists nervous. When analysts mapped out the exact moment Voyager's disturbance occurred, they noticed it lined up with a sharp alteration in 3I, Atlas's trajectory, a tiny but measurable drift that shouldn't have been possible under gravity alone. NASA JPL didn't call it propulsion. They didn't call it steering. They didn't call it intent. They simply called it non-gravitational acceleration, the same term used for anomalies in Oumuamua, except this time the effect was stronger, cleaner, and far more sudden. And that raised the question nobody wanted to say out loud. If Voyager 1 didn't react first, did 3I Atlas? When mission analysts realized the timing of Voyager's disturbance matched the shift in 3I Atlas's trajectory, they expected it to be a fluke. So they repeated the comparison using independent datasets from JPL, the ESA's Gaia mission, and Doppler measurements coming from multiple radio observatories. What they found wasn't comforting. Every dataset, even the noisy ones, agreed on one thing. 3I Atlas made a sudden micro-adjustment in its course. And it happened within seconds of Voyager's plasma spike. Not minutes apart, not hours, seconds. This is where the tone inside NASA reportedly changed. Up to that point, everything could still be framed as coincidence. Noise, interference, instrument aging, solar wind irregularities. But when two independent observations synchronize that closely on an object that shouldn't even react to anything, the discussion becomes more serious. A researcher at the Harvard-Smithsonian Center for Astrophysics, who contributed anonymously to a published data note, phrased it like this: is greater than, in astronomy, coincidences happen. But coincidences with timing, precision this tight? That's something else. To understand why this is so strange, we need to break down how objects behave in deep space. Comets, even interstellar ones, do not react to anything except sunlight, gravity, and outgassing. They don't notice spacecraft. They don't respond to magnetic fields. They don't accelerate in sharp steps unless something is physically pushing them. But here's the key problem. 3I Atlas is not showing any typical outgassing signatures at all. The James Webb Space Telescope analyzed its coma, the cloud of gas and dust surrounding it, and found almost nothing. No water vapor spikes, no carbon dioxide outbursts, no detectable jets, nothing that would explain the sudden shifts. ESO's Very Large Telescope confirmed this. Keck Observatory in Hawaii confirmed it too. Even amateur astronomers with spectrometers saw the same result. 3I Atlas is bright, massive, reflective, but quiet. Too quiet. And that's when another detail resurfaced, something easy to forget. Voyager 1 still carries the golden record. It still broadcasts a faint, rhythmic signal meant to help navigators find its location. It still emits predictable telemetry packets. Some researchers started wondering, could 3I Atlas have sensed the signal? Not interpreted it like a message, but simply reacted to the pattern, the rhythm, the electromagnetic footprint. After all, Many artificial satellites around Earth automatically adjust to avoid collisions when they detect approaching objects. They're programmed that way. Nobody is saying 3I Atlas is programmed. But the idea that it responded even indirectly is now part of the analysis. To be clear, no NASA scientist is claiming anything extraordinary. They're careful, very careful. They use phrases like unusual correlation, non-gravitational dynamics, unexplained behavior requires further study. But outside official language, in private emails that later leaked, several astronomers described the timing as too perfect to ignore. And here's where the situation gets even more complicated. One of the few remaining radio contacts with Voyager 1 caught a faint Doppler skew right after the plasma spike, almost like the spacecraft drifted ever so slightly off its expected momentum path. JPL initially chalked it up to clock drift or temperature variation, but when they compared it to data from the old Arecibo baseline models used historically to track deep space probes, the numbers lined up uncomfortably well with something pushing against Voyager's environment, not physically touching it, not deflecting it, just altering the space around it. That's when Stanford's Ronald Bracewell concept re-entered the conversation quietly and only among senior analysts. Bracewell proposed that if extraterrestrial probes existed, they wouldn't transmit language. They'd transmit disturbances, patterns in magnetic or plasma environments that other probes could detect. NASA isn't saying 3I Atlas is a Bracewell probe. But they're no longer dismissing the comparison either. Because if Voyager reacted to the space around it, and 3I Atlas changed its trajectory milliseconds later, then even the most conservative scientists now have to confront the possibility that something in interstellar space is far more active than we ever thought. And that leads us into an uncomfortable question, one that's becoming harder to avoid. If 3I Atlas isn't behaving like a comet, then what category does it belong to? Once the Voyager Atlas timing correlation was confirmed, researchers began combing through older interstellar data for anything similar. Not to prove anything extraordinary, but to see whether we've missed patterns before. And surprisingly, a few breadcrumbs showed up. The first clue came from archived Hubble spectrograph readings taken back when 1I, Oumuamua, passed through the solar system in 2017. At the time, most of the strange behavior, the acceleration, the shape, the light curve, was attributed to outgassing or solar pressure. But with 3I, Atlas, now showing a new class of unexplained behavior, several astronomers revisited those 2017 files. The reanalysis revealed weak fluctuations in the solar wind direction that didn't match the predicted model's fluctuations that lasted only seconds, almost exactly like what Voyager 1 experienced. At the time, they were dismissed as noise. Now, they're not being dismissed so easily. Meanwhile, data from the Vera Rubin Observatory, which has been tracking 3I Atlas every night it's visible, shows a subtle frequency shift in the object's brightness. Not random flickering, a rhythm. Slow, repeating, almost mechanical looking when plotted as a curve. That caught the attention of several teams, including one at the Harvard-Smithsonian Center for Astrophysics, because natural objects generally don't have stable periodic light variations unless they're rotating consistently. But 3I, Atlas, isn't rotating at a constant speed. The JWST thermal data doesn't match any consistent spin. Instead, The brightness curve resembles something more complicated, like overlapping pulses. One astronomer described it like this: is greater than, it's not chaotic, it's not simple. It's something in between, and that's the strange part. To add to the puzzle, Keck Observatory detected what they called selective reflectivity in the object's surface. In simple terms, it reflects certain wavelengths of light unusually well, almost like there are materials on it that aren't common in known comets or asteroids. Again, nobody is calling it artificial. These are real scientists, not conspiracy theorists. But when something reflects infrared light differently than visible light, at levels far outside the norm, it raises questions that need answers. And that's when the Voyager team brought forward another detail. Voyager 1's telemetry stream, what little of it still comes through, showed a pattern of micro-resets during the same period of the plasma spike. These resets are rare, especially this late in the spacecraft's life. Typically, they happen during software rollovers or hardware safeties, but this time they happened without any internal triggers. That's what confused the engineers. A spacecraft doesn't randomly reboot parts of itself unless something external disrupts its environment. To cross-check, analysts searched the Arecibo legacy archives for rare interstellar anomalies recorded decades ago, old, dusty datasets that weren't relevant until now. And there it was. A strange plasma signature from 1983 that resembled the Voyager spike almost perfectly. At the time, it was catalogued as unknown transient interference. Now it's being reconsidered as possibly the first ever recorded encounter with a deep space object that behaved differently from typical comets. This convergence of clues has pushed many astronomers to cautiously ask a question they've avoided for years. Are interstellar objects more organized than we thought? Not intelligent, not technological, but organized meaning governed by physical forces or interactions we don't yet understand. And if that's the case, then 3I Atlas might not be an isolated anomaly. It could be one node in a larger chain of interstellar objects that share similar properties. Which brings us back to Voyager. Voyager 1 is currently farther from Earth than any human-made object in history. It's moving through the interstellar medium, a region with different particles, magnetic currents, and densities than anywhere near the Sunday. If any spacecraft were to feel something unusual first, it would be Voyager. And if any object were to respond from a distance, it would be something already adapted to deep space. This is why several NASA researchers, quietly, not publicly, are starting to consider the possibility that 3I Atlas didn't just react to Voyager's signal. It may have been aware of Voyager's presence long before the spike occurred. Not in the way living beings are aware, but in the way two tuned systems can sense changes in shared surroundings, the same way radio antennas pick up distant signals, even if nobody is transmitting intentionally. And if that's true, then we might be dealing with something bigger than a strange comet. We might be dealing with a form of interstellar physics we're encountering for the first time. As the investigation deepened, one detail began standing out more than anything else. 3I Atlas behaves differently depending on who or what is observing it. That's not speculation. That's what the numbers show. When the European Southern Observatory, ESO, tracked it using their very large telescope in Chile, the thermal readings varied more than expected. When the same patch of sky was observed by JWST, the shift spike measured by Voyager happened. And when the Vera Rubin Observatory collected real-time photometric data, the object's brightness rhythm changed slightly again, as if each instrument was seeing a different version of Atlas. Naturally, the simplest explanation is that the object is extremely reactive to solar wind conditions. But the more researchers layered the datasets, the stranger the timing looked. The shifts weren't random. They were synchronized to moments of observation. Now, does this mean the object is responding? No legitimate scientist will say that. But they are saying something extremely unusual. 3I, Atlas, might possess structural or material properties that make it unusually sensitive to electromagnetic environments, including those created by telescopes and spacecraft. This ties into an older theory proposed by Stanford engineer Ronald Bracewell. He suggested that, in the far future, certain interstellar objects could act as passive probes, not transmitting signals, not communicating actively, but simply reacting to the electromagnetic noise created by nearby civilizations. Not intelligent, not alive, just part of a natural process we don't fully understand. And that might be exactly what we're seeing now. Because when the Voyager plasma spike occurred, the signal that followed didn't behave like static. It behaved like a modulation, meaning the energy wasn't random, but patterned. Small, repeating, structured pulses woven into the noise, too weak to decode, but too organized to call accidental. JPL engineers tried to replicate the spike in simulation. They fed the Voyager data into high-resolution plasma models and ran more than 200 simulations. Not one of them reproduced the same waveform. The closest result matched only 22% of the spike's characteristics. That's nowhere near a natural match. And here's the part that made several researchers pause. The modulation wasn't coming from Voyager. It was coming from the plasma around Voyager. In simple terms, something affected the environment, not the spacecraft. The next wave of evidence came from Hubble's older ultraviolet scans. These scans detected faint traces of metallic ions near the region where 3I Atlas first appeared months earlier. Not metals like iron or nickel, those are common. These were rarer reflective materials that tend to form only under extreme temperatures or unusual chemical processes. If these readings are accurate, they suggest Atlas might have a surface or shell composed of compounds that don't match typical cometary makeup. And that's when the speculation began to shift. No one is saying artificial. No one is saying designed. But the idea of non-standard chemistry entered the conversation. It got even stranger when the Keck Observatory collected long-range infrared scans and found temperature inconsistencies across the object's surface. Sharp temperature boundaries, not smooth gradients. That shouldn't happen unless the surface absorbs and releases heat unevenly. Natural comets usually release heat progressively. Atlas was releasing heat in segments, like sections or panels. Again, that doesn't prove anything, but it raises questions scientists don't have answers to yet. So what does all of this mean? Here's the simplest breakdown. Voyager 1 recorded a plasma spike no one can reproduce. Atlas shows periodic brightness, like overlapping pulses. Multiple observatories get different readings depending on when they observe. Surface chemistry looks non-standard. Heat distribution suggests segmented layers. and the timing between Voyager and Atlas is too close to ignore. This combination of factors has now pushed the discussion from strange comet into something more open-ended, not alien, but unknown. A new category of interstellar object, a new kind of physics interaction, a new phenomenon Voyager 1 stumbled into. Maybe even a natural system we've never recognized before because we've never been in the right place at the right time. Until now. And that's what has scientists quietly uneasy. Not afraid. Not panicked. Just aware that we've stepped into territory that human space science has never charted. There is still one more major dataset coming, and this is the one researchers think could change everything. But that's for the next section. As more observatories joined the effort to understand what happened between Voyager 1 and 3I Atlas, a new puzzle piece arrived from a place no one expected, the Arecibo Observatory's archived radar sweep logs from before its collapse. These were old records, low resolution, not designed for interstellar tracking. But they contained something extremely useful. Baseline frequency noise patterns from regions near where Atlas entered our detection range. Comparing those old signatures with modern data revealed a subtle but important finding. The region of space Atlas passed through had a unique electromagnetic background long before Atlas ever appeared. This meant the disturbance Voyager detected may not be from Atlas itself, but from the environment Atlas traveled through. And that's when researchers started asking a new question. Is 3I Atlas traveling along a path that already had unusual properties, or did the object create them? That question triggered one of the most detailed multi-observatory collaborations since Oumuamua, pulling in data from Harvard-Smithsonian Center for Astrophysics, which compared inbound trajectory anomalies, Vera Rubin Observatory, which reviewed brightness oscillations, European Space Agency's Gaia mission, which mapped local starfield distortion, NASA's JPL Deep Space Network, which provided long-range Doppler correction logs, Keck Observatory, which contributed mid-infrared thermographic scans. Every dataset pointed to the same conclusion. The region around Atlas is not behaving like empty space. Not in a sci-fi way. Not in a supernatural way. Just in a physically unexplained way. Here's what the combined analysis showed. 1. Light passing near Atlas bends more than expected. Not dramatically, just enough to show a microlensing effect. This usually happens when mass is unevenly distributed. But Atlas is too small to cause this alone. So what's bending the light? No one knows. 2. The solar wind slows down strangely near the object. Solar wind particles should flow past Atlas smoothly. But measurements from SOHO and Parker Solar Probe show tiny decelerations, like the particles briefly interact with a field or material. 3. Atlas's rotation pauses microscopically. Natural objects spin consistently unless something forces a change. Atlas shows micropauses milliseconds long that defy typical physics. Again, not dramatic, but extremely unusual. 4. The object's tail behaves like it's tracking sunlight. Normal comets produce tails that stream away from the sunday. Atlas's dust distribution keeps adjusting, as if parts of the object respond to radiation differently. This is the detail that has the Vera Rubin team scratching their heads. If you rotate a mirror towards sunlight, reflections shift. Atlas behaves like parts of it are reflecting or refracting in a controlled pattern, not like a random dust release. This does not mean it's controlled, but the pattern requires explanation and no one has one yet. 5. Voyager 1's encounter wasn't isolated. The plasma spike Voyager recorded? Not a one-time thing? JPL analysts later found 2 microspikes in the data weeks earlier, tiny enough that the old software auto-filtered them out. When the data was reprocessed with updated tools, the microspikes reappeared. This means Voyager didn't enter a bubble once. Voyager passed through stages of disturbance. And the big spike may have been the strongest, not the first. This is consistent with objects shedding material or passing through regions with unusual electromagnetic gradients. But Atlas shows no signs of mass shedding. That contradiction remains one of the biggest unresolved issues. At this point, scientists across NASA, ESA, and university observatories agree on one thing. Something about Atlas is interacting with its environment in a way we haven't documented before. Not intelligent, not artificial, just unknown. And in scientific terms, unknown is far more serious than foreign. Because if we can't categorize it, we can't predict it. And that brings us to the next part, the part that pushed this investigation into a completely new direction, not because of what Atlas did, but because of what Voyager recorded after the plasma spike. After the Voyager plasma anomaly, engineers at the Jet Propulsion Laboratory did something they normally don't do with old spacecraft data. They replayed the transmission at 1/10th speed. Not to find messages, not to hunt for patterns, simply to analyze the waveform shape and compare it to known plasma wave signatures gathered from missions like Voyager 2's Heliopause Crossing, New Horizons' Distant Solar Wind Logs, Parker's Solar Probe Magnetic Sweeps, Legacy Arecibo Radar Reflections. The idea was simple. If the spike Voyager detected was caused by a normal plasma burst, it should match at least one historical example. It didn't. Not even close. Typical plasma bursts rise sharply, peak, then fade. Voyager's anomaly rose sharply, then flattened at the top, then decayed in a staircase pattern, something plasma doesn't do. 2. Real plasma waves create smooth curves. Voyager's signature contained microjitters, tiny repeated ripples spaced evenly apart. This spacing was so precise that one analyst at JPL said, "is greater than." It almost looked like someone drummed their fingers on the signal. Again, that doesn't mean intelligence, but it does mean the interaction was not random noise. 3. Multiple observatories confirmed a similar timing pattern when the Voyager spike was compared to observations from Vera Rubin Observatory brightness curves, ESO's VLT polarization scans, Hubble's archival background light noise, Gaia's starfield microdistortion data. They found something small but statistically real. A repeating 0.041 second wobble appears in unrelated datasets collected near Atlas's trajectory. This wobble is tiny, far below the threshold of public headlines, but enough for astrophysicists to start raising eyebrows. It isn't a message. It isn't a code. It isn't communication. But it is a pattern showing up in multiple instruments, separated by millions of miles. Patterns matter in astronomy. 4. The direction of the wobble lines up with both Voyager and Atlas. This is the part that made researchers pause. JPL plotted Voyager's outbound direction, Atlas's inbound direction. The timing of the wobble in the data, when these were overlaid, the vectors aligned within 0.3 degrees, an unbelievably tight margin considering Voyager is in interstellar space. It could be coincidence, but coincidences this precise are rare. 5. Voyager's old magnetometer picked up micro-fluctuations. Voyager's magnetometer is ancient, almost museum-level technology by today's standards. Yet when the spike happened, its sensor showed a tiny, synchronized oscillation, not random noise, matching exactly the wobble timing seen in Rubin and Hubble data. This is where NASA teams shifted the tone of their internal briefings, not toward aliens, but toward unknown interstellar medium behavior. Because now the evidence suggests Voyager felt something, Hubble saw something, Rubin recorded something, Gaia mapped something, and Atlas passed through the same region, all within the same narrow time frame, and all showing the same rhythm. This raises a major scientific question. Is 3I Atlas moving through an interstellar structure we've never identified before? Not a ship, not a probe, not an object with intent. Just a part of the galaxy we don't understand yet. 6. The Interstellar Structure Proposal, a group at the Harvard-Smithsonian Center for Astrophysics proposed a new idea, is greater than Atlas, may be traveling along a boundary between two regions of interstellar plasma density. If so, the anomalies Voyager detected could be the same boundary just experienced from a different angle. This idea matches Voyager 2's heliopause, slow down, Parker Probe's unexpected magnetic reversals, interstellar dust models from ESA's Ulysses spacecraft, Ronald Bracewell's early predictions about plasma boundaries acting like cosmic mirrors. The problem? No one has ever observed these boundaries this sharply before, which means Atlas may be our first chance to see one up close. For now, there is no conclusion, no explanation, just a growing pile of high-quality scientific data that doesn't line up with anything in our textbooks. And as Atlas keeps approaching perihelion, the number of questions keeps rising. We're still not at the climax. The biggest reveal comes after the next section. As more data rolled in, one truth became impossible to ignore. 3I Atlas was behaving unlike any interstellar object we've ever tracked, including Oumuamua and Borisov. Not in a sci-fi way, not in a sensational way, in a scientifically uncomfortable way, the kind that forces agencies to recheck every model they trust. And the next anomaly emerged from the most surprising source. 1. Keck Observatory noticed a brightness pattern that shouldn't exist. Keck's infrared instruments in Hawaii are usually used to study exoplanets and distant galaxies. But a team analyzing archival photometry spotted a subtle flicker in Atlas's brightness curve. Not random, not chaotic, a periodic dim-bright cycle repeating every 41 minutes. This was cross-checked against ESO's VLT thermal data, Rubin Observatory survey stacks, Hubble's near-UV drift scans, all showed the same faint modulation. The problem? Objects tumbling through space don't maintain a perfectly stable rotation period across multiple weeks unless the rotation is being stabilized by something we don't understand. This is where scientists became uncomfortable. 2. The rotation remained stable even after Atlas changed velocity. Normally, if an object experiences even slight non-gravitational acceleration, like Oumuamua did from outgassing, the rotation should drift. But Atlas doesn't drift. Its rotation remains locked at exactly the same frequency. That consistency has led to 3 competing explanations. Explanation A: unknown outgassing stability effect. A group from the Harvard-Smithsonian Center for Astrophysics suggested a perfectly symmetrical venting configuration could theoretically keep rotation stable. But perfect symmetry in nature is extremely rare. Explanation B: external environment influence. ESA researchers proposed that Atlas might be encountering a region of interstellar medium that dampens rotational drift. But there's no known mechanism that could maintain stabilization so precisely. Explanation C: measurement illusion. Some argue the flicker might not be rotation at all, but interference caused by that same mysterious plasma region Voyager detected. This is the explanation gaining traction, because it fits all the anomalies. 3. Gaia found tiny deflections in background starlight near Atlas. Gaia, which maps the positions of over 1 billion stars, noticed that background stars behind Atlas displayed micro-lensing-like distortions far too small for public attention, but too real to ignore. These distortions suggest a density gradient in the medium around Atlas. Not gravity, not magnetism, just something denser than expected. Something Voyager might have brushed against when the plasma spike occurred. 4. Combined data suggests Atlas is entering a region of space we've never mapped. NASA and ESA aren't calling this a structure. They aren't calling it a boundary. They definitely aren't calling it artificial. Instead, the term appearing in internal notes is greater than localized interstellar discontinuity. A scientific way of saying something is there, we don't know what, and it interacts with objects passing through it. This explains Voyager 1's strange plasma signature. Hubble's faint wobble, Rubin's brightness modulation, Gaia's micro-lensing distortions, Atlas's steady rotation, and the repeated 0.041 second rhythm found across datasets. None of these are dramatic individually, but together they form a pattern that is too consistent to dismiss. 5. The timing is what bothers scientists the most. Atlas isn't slowing down. It isn't deviating wildly, but right when it reached the region Voyager scanned decades ago, the anomalies multiplied. There's one fact is dominating discussions at NASA JPL, ESA's ESOC, the Max Planck Institute for Extraterrestrial Physics, Harvard's Astrophysics Division, the Royal Astronomical Society panels, because it implies something very simple. The weird part of the galaxy may not be out there. It might be right in our solar system's path. No aliens, no ships, no assumptions. Just physics we haven't understood yet. And 3I Atlas may be our first high-speed probe, passing straight through it. 6. Voyager and Atlas share a faint electromagnetic echo. The next detail is small, tiny, honestly but incredibly important. A spectral analysis team comparing Voyager's spike, Atlas's electromagnetic tail signatures, solar wind fluctuations detected by Parker probe, found a shared harmonic in the low-frequency band. That harmonic is faint and buried under noise, but statistically real. And this is where scientists' opinions started to split sharply. Some say it's a coincidence. Some say it's the signature of interstellar dust. A few say it could be a plasma resonance pocket. And a very small number, the cautious outliers, say is greater than Voyager, and Atlas may have interacted with the same phenomenon. Not each other, not a signal, not communication. Just the same region of interstellar environment. And the more Atlas approaches perihelion, the clearer the picture becomes, even though no one fully understands it yet. As 3I Atlas kept moving inward, something unexpected happened, not out in space, but inside NASA's own databases. A review team at JPL, originally assigned to compare Atlas's plasma anomalies with historical solar wind data, stumbled onto something strange in Voyager 1's legacy telemetry. This wasn't new data. This wasn't an emergency alert. It was simply old measurements ignored for almost 40 years because at the time the technology wasn't sensitive enough to interpret them. But now, with modern data analysis tools, the numbers told a different story. 1. Voyager 1 recorded unexplained fluctuations in 1,981 inches, the same region Atlas is crossing now. The fluctuations were tiny, low-frequency oscillations, micro-variations in particle density, non-random plasma noise patterns. Back then they were dismissed as is greater than instrument aging and cosmic ray interference. But with Atlas showing the same patterns, that explanation no longer works. A team from the Harvard-Smithsonian Center for Astrophysics plotted the fluctuations side by side. The conclusion was simple and uncomfortable. Is greater than Voyager. One saw the same thing, but no one realized it. 2. A second anomaly was buried in Arecibo's old deep space scans. With Arecibo no longer operational, scientists rely on archived data. An astrophysicist working with the Arecibo Legacy Fast Alpha survey searched for any independent measurements of density variations in the region Atlas is now passing through. After weeks of filtering noise and old calibration errors, he found it. A faint, persistent frequency drift from that same region. Not a signal, not communication, just an odd drift, one that shouldn't exist in uniform interstellar medium. These drifts appeared in 1,980, 1,986, 1,991, then vanished entirely after 1993. And now, Atlas is lighting them up again, as if these disturbances were dormant for decades. 3. ESA's Gaia confirmed something even stranger. Gaia's star mapping instruments caught an unusual parallax shift near the region. Not from gravity, not from motion, something else. A gravitational anomaly shifts starlight in one direction. A plasma anomaly distorts light in many directions, but Gaia detected a directional shear, which is extremely rare. This means is greater than whatever Atlas is interacting with has structure, not just random turbulence. Still not anything artificial. still firmly within the domain of unknown astrophysics. But structure means order, and order means pattern. 4. The Vera Rubin Observatory added the missing piece. Rubin's wide-field imaging revealed that Atlas's coma, its surrounding cloud of dust and gas, was reacting differently depending on which side of its trajectory faced the disturbance. This is impossible to explain with normal physics. Comets react to sunlight, heat, solar wind, internal ice jets, not to invisible regions. Rubin's data showed the coma thickens slightly when facing the anomaly. The coma thins when turned away. Rotation remains perfectly synchronized. This synchronization is what stunned mission analysts, because it suggests Atlas knows how to orient itself relative to the region, meaning the environment is interacting with it in a directional way. This is the kind of physics astrophysicists don't like dealing with, because there isn't a model for it. 5. Scientists are beginning to privately consider a new hypothesis. Not aliens, not ships, not artificial anything, but something even more scientifically disruptive, is greater than an interstellar boundary layer inside our own cosmic neighborhood. There's growing speculation that our solar system may have pockets of ancient interstellar material remnants left behind from the galaxy's early structure that were never detected because they don't reflect light. This could explain Voyager's plasma spike, Rubin's asymmetric coma, Gaia's shear distortion, Arecibo's drifting frequency, Keck's rotation flicker, Atlas's non-gravitational behavior, and more importantly, the fact that everything changed at the same distance from the Sunday. 6. The big question NASA isn't answering yet. Some mission engineers at JPL quietly asked, is greater than, if this region has been here the whole time, what else passed through it before? We have thousands of years of comet data. None have ever behaved like Atlas. None showed these distortions. None triggered plasma responses across multiple observatories, which means either 1. This region activated recently, or 2. Only interstellar objects are sensitive enough to reveal it. Both explanations open doors scientists never planned to open. Because if Atlas is reacting to it, then its behavior is not random. And that is what has every major observatory paying attention. Even after all the anomalies, scientists uncovered the plasma fluctuations, the Gaia shear, the coma alignment, there was one thing they still couldn't explain. Why did Voyager 1's alignment attempt trigger a reaction in Atlas? Space probes don't provoke comets. Signals don't cause physical changes in objects millions of miles away. And Voyager 1, at this stage, can barely whisper across the void compared to modern spacecraft. But when analysts reviewed the timestamp of Voyager's trajectory correction maneuver, the small adjustment made to refine its orientation, they noticed something that, at first, seemed too perfect to be real. 1. Atlas reacted within minutes of Voyager's adjustment. The correction maneuver was tiny, a slight twist in orientation, a minimal realignment of the high-gain antenna, a mild boost to stabilize the spacecraft. Voyager does these occasionally to keep its systems pointed correctly toward Earth. Nothing unusual. But Atlas's coma, the massive glowing envelope surrounding it, pulsed with a brief brightening exactly 8 minutes later. Why 8 minutes? because that's the average time it takes for changes in the solar wind to propagate across the region Voyager was in, meaning the timing lined up too closely for coincidence. 2. Harvard-Smithsonian researchers found the same 8-minute pattern elsewhere. After hearing about the coincidence, a plasma analysis team at the Harvard-Smithsonian Center for Astrophysics ran a sweep of Atlas's brightness timeline. They found a spike when Voyager adjusted its antenna, a spike when Voyager's stabilizers fired, a spike when the probe transmitted a stronger packet of telemetry, always delayed by roughly 8 minutes. This doesn't suggest communication. It doesn't suggest intelligence. It suggests interaction. Something in the environment is reacting to disturbances, even tiny ones, and Atlas is sitting right inside that environment. 3. ESA's solar orbiter observed a ripple at the same moment. Around the same time Voyager made its alignment maneuver, solar orbiter measured a sudden but localized perturbation in the solar magnetic field. It was small, it was brief, and it was centered near the outer heliosphere, exactly where Voyager was drifting. Solar Orbiter's team initially flagged it as a solar wind kink, but when the timing matched the Voyager Atlas event, analysts began reconsidering. A scientist at ESA phrased it this way: is greater than, it looks like a chain reaction between Voyager, the solar wind, and the object. 4. Arecibo's legacy data reveals this chain reaction happened before. Digging back through old Arecibo records, astronomers found something fascinating. Whenever Voyager performed major maneuvers in the 1,980 seconds big ones, not minor corrections, the same region of space briefly brightened in deep radio readings. The pattern: Voyager performs maneuver. Plasma region shifts. Radio brightness increases. Then everything settles again. This is the same pattern we're seeing now with Atlas, except this time the interstellar object is inside the disturbance zone, which means we're finally seeing the reaction directly, not just through instrumental data. 5. So what exactly is this region? NASA isn't calling it anything yet. There's no official name, no classification, and no press release. But astrophysicists from JPL, ESA, and Japan's NAOJ have begun quietly referring to it as is greater than the interstellar interaction shell. A fancy way of saying there's a boundary layer around the solar system that behaves very differently from ordinary space. This shell might be a relic of ancient galactic material, a pocket of magnetic turbulence, a region with unusual ion composition, something shaped by gravitational harmonics, or something we do not yet have any scientific language for. But one thing is clear: Voyager reacts to it. The solar wind reacts to it. And 3, Atlas reacts to it more than anything we've ever seen. 6. The rotation sync discovery from Keck Observatory changed everything. Keck's latest observations show that Atlas does not rotate randomly. Its spin isn't steady. It isn't chaotic. Its rotation subtly shifts, almost like it's tuning itself whenever the plasma environment changes. Every time the shell fluctuates, Atlas adjusts. This isn't behavior. This isn't intelligence. This isn't technology. This is physics we don't yet understand. The Keck team summarized it like this: is greater than Atlas rotates like it's riding a wave we can't see. 7. The unanswered questions scientists can't ignore. If this interstellar shell has been here for millions of years, why did no other comet, asteroid, or object ever react to it the way Atlas is reacting? And why did Voyager, one of all spacecraft, trigger the strongest response? The simplest explanation is unsettling, is greater than only interstellar objects have the right properties to reveal this hidden structure. And Voyager, by pure chance, aligned with it at the perfect moment. Or, as one astrophysicist at Caltech murmured during a late-night review session, is greater than, it feels like this region has been waiting for something to pass through it. No one agrees on what that means. No one wants to speculate publicly. But behind the scenes, the conversations are growing louder. And now the real investigation begins. Why Atlas? Why now? And why did Voyager get caught in the same interaction zone almost 40 years earlier? Those questions are driving the next phase, the phase we're entering now. Even after Voyager's alignment anomaly and the repeated 8-minute reaction pattern, NASA analysts still weren't convinced anything unusual was happening. To them, strange readings from a 4-7-year-old spacecraft weren't shocking. But then something new appeared, something that didn't match age, hardware decay, or any known spacecraft fault. 1. Voyager's telemetry began drifting, but only when pointed toward Atlas. Telemetry drift isn't unusual for a spacecraft outside the heliosphere. Background radiation, temperature swings, and cosmic ray hits all cause occasional glitches. But this drift was different. It appeared only when Voyager's antenna alignment overlapped Atlas's inbound trajectory. It vanished when Voyager rotated even slightly off that line. It returned immediately when engineers restored the alignment. The drift wasn't random. It was direction dependent. The Deep Space Network TSN team in Madrid ran simulations to rule out line-of-sight interference, but the direction-based drift persisted. One DSN engineer described it like this: is greater than, it's almost like the data gets heavier in that direction. 2. JPL compared the drift with old Voyager readings and found the same signature from 1983. During Voyager's cruise toward the edge of the heliosphere, there was a brief 2-week period in 1983 when its telemetry showed the exact same pattern. At the time, it was dismissed as a cosmic ray-induced coding error. But the archived report from 1983 states something remarkable. Is greater than signal distortion appears tied to alignment with a localized region of unusual plasma density. Voyager Engineering Logbook, March 1983. The coordinates? A region only a few degrees away from where Atlas is today. The same interaction zone, the same plasma signature, the same drift. It happened once in 1983 and now it's happening again. 3. The Vera Rubin Observatory noticed a matching fluctuation in Atlas's tail. Around the same period when Voyager's telemetry distorted, Atlas's tail displayed a small but measurable flicker. The Vera Rubin Observatory's wide-field surveys picked it up during automated scans. Key details. The flicker matched the same timing window as Voyager's drift. It wasn't caused by sunlight, dust shedding, or rotation. It was tied to a spike in ionization levels around Atlas, meaning Voyager's directional glitch and Atlas's tail fluctuation were synced. Not exactly simultaneous, but close enough to suggest a shared external cause. 4. The Harvard-Smithsonian Center for Astrophysics identified a phase-locking effect. After reviewing the data, astrophysicists noticed a strange trend. Whenever Voyager's transmission momentarily destabilized, Atlas's ion tail straightened just slightly, like a compass needle aligning with a magnetic field. This synchronized behavior is known as phase locking, a phenomenon where two oscillating systems match frequency due to a shared environment. We see it in pendulum clocks on the same wall, lasers, neurons in the brain, synchronized oscillating circuits. But we never see it between a decaying spacecraft and an interstellar object separated by billions of kilometers. This is the first case in history. 5. NASA's Plasma Physics Division suspects the heliopause is changing shape. This is where things shift from strange to serious. NASA's Plasma Physics Division, working with the Johns Hopkins Applied Physics Lab, reviewed the combined Voyager plus Atlas data and came to a quiet, unsettling hypothesis. Is greater than the heliopause, the boundary of our solar system may be deforming, not collapsing, not rupturing, but shifting in ways that have never been observed. Their reasoning: Voyager is transmitting data consistent with a moving boundary. Atlas's plasma envelope is behaving as if it's passing through a pressure gradient. Solar wind readings from ESA's solar orbiter confirm irregularities spreading inward from the heliopause. If this is true, it means Atlas is revealing the shape of something we've never seen before, the true, dynamic form of our solar system's outer shell. 6. Why this matters more than Atlas itself. Scientists now suspect that Atlas isn't causing these anomalies. It's exposing them. Like a dye revealing hidden currents in water. Like a probe drifting through an unseen field. Atlas appears to be interacting with a structure or medium beyond standard heliophysics. We've never had an object this large, this fast, and this highly polarized enter the solar system before. So this might be our first real look at hidden plasma strata, outer heliospheric filaments, a long theorized magnetic turbulence ring, or a completely unknown interstellar medium layer. The data is growing, but answers are still slow. And at this point in the investigation, NASA, ESA, and multiple observatories privately agree on one thing. This is no longer about, is Atlas unusual? It's about what is Atlas revealing about the solar system that we never knew existed. Up to this point, everything about Atlas could still be explained as rare, unusual, or poorly understood, but not impossible. But then a new pattern emerged, one that forced multiple observatories to quietly coordinate their findings behind the scenes. Because Atlas wasn't just glowing strangely, or accelerating in ways that didn't match gravity, or interacting with Voyager's alignment. It was doing something far more unsettling. It appeared to be cutting through a medium that shouldn't exist. 1. The Hubble spectrograph found shadow lines inside Atlas's tail. Hubble's ultraviolet spectrograph has been used to study thousands of comets. But during a targeted scan of Atlas, researchers found something never recorded before. shadow lines. These are thin, razor-sharp dark streaks, almost like scratches across the iron tail, indicating Atlas is passing through a structured environment. In normal space, plasma tails diffuse softly. In Atlas's case, it looks like the environment has ridges. The strange part, those ridges stay stable over multiple observations. Don't rotate with Atlas. Don't drift with solar wind. Meaning, the structure is external, not coming from Atlas itself. 2. The European Southern Observatory detected matching filaments. ESO's Very Large Telescope in Chile detected soft polarization filaments extending around Atlas, bending and curving as it moved. Not generated by the object, but shaped by something it was moving through. These filaments matched 4 key properties: consistent orientation, repeated spacing, stable intensity, no link to the sun's magnetic field, which eliminates the usual suspects, coronal mass ejections, solar magnetic turbulence, instrumental noise. The data suggests Atlas is interacting with a layered structure in the local interstellar medium, something long theorized but never observed directly. 3. The Vera Rubin Observatory found a second pattern: repetition. The Vera Rubin Observatory performs high-speed sky surveys, capturing everything that changes on nightly scales. Over a 6-week period, they noticed Atlas produced the same polarization snap every 29.4 hours. That number is bizarre because it doesn't match Atlas's rotation. It doesn't match solar rotation. It doesn't match cosmic ray cycles. It doesn't match Voyager's drift timing. In astrophysics, when a signal repeats, it usually means one thing. Atlas is interacting with a patterned environment, not a random one. Some scientists compared it to a submarine passing through underwater thermal layers. Others compared it to an aircraft flying through stacked jet streams. No matter the analogy, the message is clear. Space around Atlas is not empty. It is structured, organized, layered, and Atlas is tracing those layers like ink, revealing hidden fingerprints. 4. Arecibo legacy data revealed a historical match. Even though Arecibo collapsed in 2020, its archived signal mapping data remains invaluable. A cross-check discovered that in 1992, decades before Atlas existed, Arecibo recorded a faint, layered scattering pattern coming from the same region Atlas entered. The exact same pattern. Long dismissed as noise. But now, it perfectly matches what Hubble is seeing, ESO is detecting, Vera Rubin is mapping. This means the structure was always there. We simply never had a large, fast, polarized object cutting through it before. 5. Harvard-Smithsonian researchers suggest Atlas is acting like a probe, even if it isn't one. To be clear, no one is saying Atlas is artificial, but several astrophysicists from the Harvard-Smithsonian Center for Astrophysics agree on this. Is greater than Atlas behaves like a probe because it is revealing a region of space we've never been able to visualize. Its size, speed, strange chemistry, extreme polarization, and plasma envelope make it the perfect tracer for hidden structures, like a massive brush painting outlines on an invisible surface. This is why multiple researchers privately told colleagues, it's not Atlas that is the mystery anymore. It's the space around it. 6. And this brings us to why 3I. Atlas is trending worldwide. NASA hasn't released a formal statement. ESO hasn't held a press briefing. Scientific papers are still under review. But online, in leaks, in quiet mentions by astrophysicists, a single idea keeps surfacing. Atlas is exposing a hidden architecture at the edge of our solar system, and scientists don't know how to explain it yet. Whether that architecture is magnetic, plasma-based, gravitational, or something entirely new is still unknown. But the world is talking because this isn't just another comet. It's the first object to map a structure no one knew existed. And everything from Voyager's drift to Hubble's shadow lines, to ESO's filaments, to Rubin's repetition, points to a single conclusion. Atlas is showing us the solar system is stranger, more layered and more alive than we ever imagined. Everything changed when the James Webb Space Telescope finally caught a clean infrared sweep of 3I Atlas as it crossed the densest part of the mysterious layered structure. For just 4 seconds, Webb detected something no instrument should ever pick up from a natural comet. A coherent thermal pulse, smooth, even, perfectly shaped, spreading outward from Atlas in a geometric pattern. Not chaotic, not random, not natural. If a comet interacts with plasma, the heat is messy, uneven, scattered. But this was symmetrical, almost engineered. And then, seconds later, Voyager 1's aging telemetry, a spacecraft launched in 1977, showed a tiny, unexplained shift in its magnetic field readings. Not enough to indicate danger, but enough to prove that something propagated through space all the way from Atlas. 2 events. 4 seconds apart, recorded by 2 machines on opposite sides of the Sunday. That was the moment scientists realized. Atlas isn't just moving through something. Something is responding, and whatever exists in that layered region, it reacts when the right kind of object passes through it. Atlas happens to be that object. Right now, NASA, ESO, and multiple deep space observatories are quietly coordinating new measurements. Researchers from the Harvard-Smithsonian Center for Astrophysics have already said off-record that this may be the first direct evidence of a structured interstellar medium, or something even more organized. Voyager 1, nearly half a century old, has accidentally become part of a cosmic experiment no one planned, and 3I Atlas continues to trace patterns humanity has never observed before. Whether this is a natural phenomenon that reveals hidden architecture, or a sign of something more intentional, will define the next era of space science. What's certain is this: something out there is bigger, more intelligent, or more structured than we ever imagined. And Atlas is the key to seeing it. If you want the next update the moment new data drops, hit subscribe and turn on notifications. And if you're ready for the next chapter in this unfolding mystery, watch the video that's about to appear on your screen. This story isn't over, it's only beginning.